Hello, my name is Jeff Kramer, and today I'll be presenting Lab 3, Magnetic Field of a Bar Magnet. This lab report will be split into three primary sections. There will be an introduction that deals with the purpose, concepts, and results. There will be a measurement and calculation section that will deal with the observed data and the results of the calculations. And finally, there will also be a computational glow script model, which will deal with the code and the visual model created to model the magnetic field of the bar magnet. Let's get started and address the purpose of this experiment and the relevant fundamental physics principles, as well as a brief overview of the major results. The purpose of this lab was to create a visual representation of magnetic fields, to observe the interaction between distance and magnetic field strength. The most important concepts in this lab include the Biot-Savart law, which will enable us to compare our experimental distance dependence measurements to the predicted values, and the distance dependence equation for a magnetic field, which is commonly represented in two ways, as shown below. Now, for the results of this lab. N was equal to negative 3.324 meters, and the magnetic dipole was equal to 1.19 amperes times meters squared. Now, let's move on to the measurements and calculations section. The data were collected by using a magnetometer on a smartphone. The data at the top left show the measurements I collected for the magnetic field on the axis of the magnet, while the data at the bottom of the screen represent the measurements for the magnetic field of the axis, off the axis, or perpendicular to the bar magnet. Both tables also contain a calculated average of the magnetic field at the experimental locations. However, only the on-axis magnetic field values were graphed. This equation will be useful when we need to calculate our results, but before we start the math, I want to bring up some of the qualitative observations I collected while obtaining my measurements. Notably, as the magnetometer moved closer to the magnet, the x component of the magnetic field seemed to increase. When the magnetometer was far away from the magnet, it measured a magnetic field of almost zero along the x-axis. Another important observation I made was that we must subtract a constant value from the measured magnetic field along the y-axis in order to account for the magnetic field of the Earth. Moving back to the calculations, I used the distance-dependent equation that resulted from when we graphed the magnetic field against the distance. Using this equation and the slope of the line, which was once again negative 3.324, we can then apply the Biot-Savart law and find the magnetic dipole moment. First, we determine K by plugging in all of the values we already know into the Biot-Savart law. From the distance dependence equation, we know that Bx is equal to negative 15.27, and this allows us to solve for K, which we find is 2.33 times 10 to the negative 7th. Next, we need to set the magnitude of B bar equal to mu naught over 4 pi times 2 mu over r to the third. We can do this by replacing K times r to the n for B bar. Once again, we can simply plug in all of our known values and solve. The result of this calculation is 1.167 ampere meters squared. Finally, let's move on to the computational model section of this lab and analyze the visual model we created. The main parts of the code for these models are right here. As you can see, we had to include a function for the magnetic field, which allowed us to model what the magnetic field would be due to a dipole at various different locations. We modeled the field at numerous different locations, both on the axis and perpendicular to it, and the code calculated the magnitude of the magnetic field for each of these different locations. Now, let's take a look at our model. The purple arrow represents the magnetic field on axis, while the blue arrows represent the perpendicular magnetic field. The green arrow shows the magnetic field at a location at a 45-degree angle from the observation axis. From this perspective, only 3 blue arrows are visible, but the output of the code shows that there are 4. We can't see the 4th arrow because it's the same magnitude and direction as one of the other arrows, so they overlay. Now, I want to take this opportunity to discuss an alternate scenario for this lab. For example, if we laid out the meter stick at an angle with respect to the Earth's magnetic field, it would have significantly altered the results of our experiment, because the magnitude of the Earth's magnetic field in the x direction would no longer have been 0. We were able to avoid this non-zero x component of the magnetic field by aligning our measurements to magnetic north. In conclusion, this experiment allowed us to calculate the distance dependence of a magnetic dipole through the practical application of the Biot-Savart law. Using this, we were able to generate a model of the magnetic field of a bar magnet, visualizing how the magnet interacts with the world around it.